Melting. The heat of fusion of a solid is the amount of heat needed to melt 1 kilogram of it. It is also equal to the amount of heat given off by 1 kilogram of liquid when it hardens into a solid. It takes 335 kilojoules to melt 1 kilogram of ice into water. So it means, let's say if the solid is converting into liquid, how much ever energy is needed to convert from solid to liquid, exactly same amount of energy is released when it is converting from liquid to solid, and that is exactly 335 kilojoules. So when it is when we need to melt it, we need to supply 335 kilojoules of energy, and when it solidifies back into ice, it releases 335 kilojoules of energy. In this picture, you have an ice cube which is at 0 degrees Celsius, and it's 1 kilogram exactly. And if you are going to give 335 kilojoules of energy to this, it's going to melt all this ice into 1 kilogram of water. But look here, the temperature of the ice is 0 degrees Celsius, and also the water's temperature is also 0 degrees Celsius. So from here we can say that this energy which is given is used only to change the phase of it from solid to liquid, but the temperature of it did not change. A crystalline solid. A crystalline solid takes energy, and it is called the heat of fusion and converts into liquid. And sublimation. Sublimation is a direct conversion of the substance from solid to vapor state, or from vapor state to the solid state without entering to the liquid state. So some materials could transform from solid to vapor or gas state, and from gas state to solid state directly without entering the liquid state. That's called sublimation. As you can see in this picture, that solids can melt and become liquids, and liquids can vaporize and become solid gases, and gases can condense and become liquid, and liquids freeze and become solids. And there is a possibility of solids converting into gases, which is called sublimation, and the gases convert into solids, which is called deposition. Heat engines. A heat engine is a device that converts heat into mechanical energy or work. During the operation, a heat engine extracts energy from a flow of heat through it. Some of the heat flow is converted into mechanical energy. The rest is lost as waste heat. To produce the flow of heat energy, the heat must travel from a hot reservoir to cold reservoir. As you can see in this picture right here, so naturally the heat flows from hot temperatures to cold temperatures. So from 200 degrees Celsius, the heat flows to 20 degrees Celsius without any means of mechanical work. Let's say that, so this is a natural happening. So heat flows by itself from a hot reservoir to a cold reservoir. And when the heat is flowing from hot to cold, then you get work. The heat engine, if you connect the heat engine, then the work output will be given right here. So opposite to it is the refrigerator, where the reverse of the natural flow of heat, the work must be done by the refrigerator. You can see right here, naturally the heat will not flow from 220 to 200. So we have to do some input work, which is mechanical work, in order for the heat to flow from 20 to 200 degrees Celsius. And this is called refrigerator mechanism. The heat engine is exactly opposite of refrigerator mechanism. The idealized heat engine, so whenever you heat it up, the pressure works on top, and whenever there is any low temperatures, the pressure works from outside pressure is much higher. So whenever you heat it up, the inside pressure is higher. Whenever the temperatures are low, outside pressure is higher. The steam engine uses high pressure steam as it is high temperature reservoir, and outside air as low temperature reservoir. Gasoline engine in automobile, the ignited gases within the cylinder constitute the hot reservoir and the atmosphere is cold reservoir. A refrigerator operates as a reverse of heat engine as we just talked about, and by using the mechanical energy to force heat to flow from cold reservoir, which is the refrigerator interior, to a hot reservoir, which is atmosphere. Usually from atmosphere to refrigerator it is easier, but because of the external mechanical work, the heat flows from refrigerator to the atmosphere. Thermodynamics. Thermodynamics is the science of heat transformation. So any science which talks about the heat transformations is called thermodynamics. And the first law of thermodynamics states that energy cannot be created or destroyed, but it can be converted from one type to another type. The second law of thermodynamics says it is impossible to take heat from a source and change all of it to a mechanical energy or work. Some heat must be wasted. So, in layman's language, there is no way any machine or engine or anything could be perfectly or 100% efficient. Some of it has to be wasted. So, it is impossible to convert everything into useful energy or useful work. The maximum efficiency of a heat engine depends on the temperatures at which it takes in and ejects heat. The refrigerator, the greater the ratio between there are two temperatures, the more efficient the engines are. And efficiency is given by 1 minus T cold over T hot. So T is the temperature on the absolute scale. So let's look at one of the examples. The steam enters in a turbine at 800 degree Kelvin and leaves at 350 degree Kelvin. What is the maximum efficiency? So the cold temperature is 350 and hot temperature is 800. So just plug it in the formula. That's going to give you the efficiency of the engine. So 1 minus 350 over 800. So that will give you 0.56, so which is 56% efficiency. The fate of the universe. The heat energy of the universe increases as the as the at the expense of the other forms of energy. Heat death of the universe will occur when all the particles of matter ultimately have the same average kinetic energy and exist in a state of maximum disorder. So entropy is a measure of disorder of the particles that make up a body of matter. In terms of entropy, the second law of thermodynamics becomes the entropy of a system isolated from the rest of the universe cannot decrease. It means the entropy, which is the disorderliness of a system isolated from the rest of the universe cannot decrease. So it means it always increases. So when you look at this picture right here, that tells you if you have a falling block of ice. So if it falls, it becomes puddle and it becomes more disorderly. See, now you can see that it is a very orderly one and it becomes disorderly, and ice melts into water as its kinetic energy becomes heat when it strikes the ground. So it becomes puddle of water. And then again, this puddle of water that becomes again the vapor and goes back to the atmosphere again. So the water becomes ice and its heat turns into kinetic energy and it becomes again orderly, and it goes back to the atmosphere as a vapor. So it means like, whatever, you can see that the process that conserves the energy and increases entropy, and the process that conserves energy and decreases entropy. So in here, you can see that the disorderliness increased and then again disorderliness decreased by balancing it out. Living organisms require a constant energy input to overcome entropy and maintain the order of biological systems. So, in order for the living organisms to live properly, the disorderliness, which is the entropy, should be minimized. The entropy of the universe is increasing with the passage of time. So the entropy, which is disorderliness of the whole entire universe, is increasing as the time is passing. So this finishes the chapter 5.